Okay, so um, continuing on, um, the next force that we have that also has a functional form, um, sorry, I just want to color code this, is our spring force. So the force due to the spring is um, dependent on two pieces. It's dependent on a K value, which this thing is a spring constant. It's a value that has units of newtons per meter, and it tells you the strength of the spring. So it tells you how much force you have to exert in order to stretch or compress the spring by 1 meters. Um, these values range quite wildly. I mean, you could have a spring constant of like 10 newtons per meter, but you could also have one of 10,000 newtons per meter. So you can imagine that the springs in your suspension on your car have um, pretty high spring constant values, but maybe the spring constant in your mechanical pencil is probably not very large. So it's the spring constant, which is a parameter of the spring. So it depends on what that spring is made out of and how it's constructed. And then it's also dependent on how far away from equilibrium the spring is stretched. So you can imagine we have this spring, and right, it probably likes to exist all by itself without anything on it here at x naught. But if you take that box on the spring and you stretch it out, you have this distance here that you've stretched it. This is the delta x. So the more that you stretch it away from its equilibrium position, the more it wants to return to its equilibrium position. So this is this is the functional form of the spring force. It's related to Hooke's law, which looks just like this, except for it says F spring equals a negative K delta X, where this negative is just reminding you that if you stretch the spring, if you stretch it, then it wants to go into the negative direction. It wants to take it back to its equilibrium position. But if you compress the spring and your delta X would be a negative, then the spring wants to go again back to its equilibrium position, which would be a positive force in order to make that happen. But really for us and our purposes, we want the F spring without the negative because we'll take into account the negative or positive direction when we draw our force diagram. One more thing that I just remembered as we came back between the videos about the mu value. So these mu values are determined experimentally, and they're between different surfaces. So you'll have a mu value for wood on wood, or you might have a mu value for rubber on concrete. Okay, so the mu values are tabulated and determined based on the two different surfaces types. So it's again a quality of the actual two surfaces that are interacting with one another. Okay, so I've totally run out of room, so maybe I'll stick it up here since it's not as important as the others. The last piece that I wanted to give you, the other the other force that has a functional form is drag. So F drag actually has two different possible equations. It depends kind of on your situation on which one is most appropriate. The one that your book explores is kind of big and nasty looking. It looks like 1/4 times C sub D times rho times A times V squared, right? So a whole bunch of things that the drag is dependent on, and right, drag being that resistance that things have due to the actual physical air and atmosphere that is present. So to kind of run through these various things, the C sub D is the coefficient of drag. Again, just a value that's tabulated, typically based on like what the object is actually made out of and what its surface is like, as well as the atmosphere itself. The rho value is the density of air, because that can change depending on where you are. A is your cross-sectional area. So this is kind of just your general argument that, if you have, I don't know, a big blanket and you're using it like a parachute, that will be more effective than a little cape. So the bigger the area, the more drag that you have. And then the last parameter, the V, is the velocity. So depending on how fast you're going will depend on how substantial the drag is. And in this case, in this expression, excuse me, the drag is proportional to velocity squared. So the speed becomes a really important factor to how big the drag force is. So in general, right, you really won't need this equation, but you could, in theory, solve a problem that's dealing with drag. Okay. So this is kind of your, I don't know, laundry list of all the types of forces that you can actually compute without actually summing Newton's second law. Okay. I actually don't know how much time I have, so let me see if I can find out. That's not useful. Let's maybe try and get one more question here before the computer yells at me and tells me I have no more time. So here goes one of our ABCD questions. An object, when pushed with a net force F, has an acceleration of 2 meters per second. Now twice the force is applied to an object that has 4 times the mass. And we're being asked, what will the acceleration be? So why don't you take a moment, maybe pause the video to allow yourself time to actually think about that question and answer it on your own. So now is the time to pause the video to try the ABCD question. Okay, hopefully you've made your guess. So if I'm going to walk through this, I'm going to take that first sentence and see what I have. I have a net force of F being applied. And it produces an acceleration of 2. And so I'm just following Newton's second law that the force is equal to mass times A. Okay, but then it says, now what happens if I have twice the force is applied to an object and it has 4 times the mass? What will its acceleration be? Okay, so I just put in those new qualifiers in here. And if I'm interested in finding the acceleration, I can solve for A. So if I solve for A, I would have 2F divided by 4M. Okay, and this is only useful if I also do that on my original situation as well. If I solve for the acceleration, which was 2, I'd have F over M. And so I can replace this F over M in my second expression with the 2, because I know that ratio of the force over the mass is 2. And so the acceleration will be 1/2 times 2, and that 2 had units of meters per second squared, and so I get 1 meter per second squared. So my correct answer here ought to be B. Okay. We'll try and get another ABCD question in. We have a 40-car train travels along a straight track at 40 miles per hour. We have a skier that speeds up as she skis downhill. On which is the net force greater? So again, take a moment, pause the video, legitimately try this question just like you'd be forced to in class. And you'll have to see the next video to figure out the answer.